So what I'm saying now is that there is a function s of t such that the position of the first particle at the time t is exactly the same as the position of the second particle at the time s of t. So this is exactly the algebraic equation that corresponds to my statement that the trajectories of two particles are the same. Now, how useful is that? Well, the usefulness here comes with the ability of differentiating this equation. Because what I want to consider is I want to look at the first derivative of f and second derivative of f, first derivative of g and second derivative of g. So let me differentiate that equation with respect to t to find the first derivative of f with respect to t. Well, I can do that using the chain rule, because what I see on the right hand side is a composition. I take t, I apply the function s first, and then I apply the function g. So the derivative is going to be g prime of s multiplied by s prime of t. That's by the chain rule. But now I can find the second derivative. So I differentiate again, and I can find the second derivative of f with respect to t. Well, what I see is a product, so I have to apply the product rule. Now I differentiate the first multiplier. What's the derivative of that? It is going to be derivative of this first multiplier times s prime of t plus the first multiplier times the second derivative of s. And now what is that? How do I differentiate that with respect to t? Remember, this derivative is with respect to t. Well, I use the chain rule again. So it's going to be the second derivative of g with respect to s times the derivative of s with respect to t. And then I have to multiply that by s prime of t again. So the first term is equal to that. And the second term remains the same, g prime of s times s double prime of t. And let's look at this equation. What do I see on the left-hand side? I see a vector, the second derivative, the acceleration of the first car. What do I see on the right? What is that? That's acceleration. That's a vector. Acceleration of the second car. And what is this? Well, s of t is a function, a number assigned to a number. So derivative is going to be a number again, and the square of that number is a number. So this is just a number. And what I have is a number multiplied by a vector, making it longer or shorter. And similarly here, I have a vector of velocity of the second car multiplied by a number, making it longer or shorter. So that makes a vector equal to some vector plus another vector. So that's what equality means algebraically. But this is not the second derivative for the first derivative that I'm looking for. I'm looking for the expression of the orthogonal component of the second derivative of f with respect to the first derivative of f. Let me work that out. So first of all, what I would like to relate it to is to the vector orthogonal component of g double prime with respect to g prime. And the first step is I would replace that vector f prime with the vector g prime. Why can I do that? Well, remember the role of this vector in the formula for orthogonal component. This vector only identifies the direction of velocity. The magnitude of velocity has no value in this computation, has no influence on the orthogonal component. It is only the direction that that is important. Don't these two vectors have the same direction? Well, they do, because we know the velocity of a car, the first car, at that point is exactly in the same way as velocity of the second car. The magnitudes can be different, but directions are definitely the same. So that's why I can replace this vector with that one. And now my formula is closer to what I want, the second derivative of g with respect to g prime. But of course, the second derivative of f is not equal to the second derivative of g. You see, there are some other terms floating around. So let me just take this formula and stick it in. So I have orthogonal component with respect to g prime of the vector g double prime times s prime squared plus g prime times s double prime. Alright, now what about it? Now my next observation is that I'm looking for the orthogonal component of that with respect to direction of g prime. Now notice that adding this term proportional to g prime doesn't change orthogonal component. Orthogonal component of this vector with respect to g prime is going to be exactly the same as orthogonal component of the whole thing with respect to g prime. So that's what I'm saying. Orthogonal component with respect to g prime of the vector g double prime times s prime squared is equal to what I have there. And now finally I'm looking at this s prime squared. That's a number. And of course that number is just making that vector longer, and it is making the orthogonal component of that vector proportionally longer. That means that vector is equal to that number, s prime squared, times orthogonal component of g double prime with respect to g prime. And what we finally have is that our orthogonal component for the first car is proportional to the orthogonal component for the second car. The only question is, what is that?